Alrighty, so I want to go ahead and solve well, this is actually an appraisal thing that we did before, just to give you some more example problems for those of you that are going to be reappraising on standards. So let's get this slide here. And one. So, we're going to draw some free body diagrams here. So a ball's tossed upwards into the air before it is left the thrower's hand, and it's speeding up. Speeding up means forces are unbalanced. So I'm going to have the force of the hand going up, but I'm also going to have the force of gravity downwards, and this arrow does need to be bigger. Next, we're going to have a person on an elevator moving upwards at decreasing velocity. So that means it's slowing down, and that means the gravity force is going to overpower the normal force pushing upwards on the person. So Fg needs to be just a little bit bigger. And finally, we have a glass being pushed on a table at constant velocity. Well, that means we're going to end up having a normal and a weight, which is fine. But then the other thing is we've got a pushing force, Fp, and that's going to exactly balance the friction force. That's why it moves at constant velocity. If you just drew the pushing force, it would accelerate. So that's problem number 1. I'm going to try to do this again. This is problem number 2. So the forces do not balance, and so what that means is we're going to have the up forces, A and D, and they're going to compete with the down forces, which are E, B, and C. And the effect of these two competing sets of forces is that the mass accelerates. Next, we have horizontal forces not balancing, and then vertical do. So let's balance the vertical. That's going to be F norm balances F grav. And then in the horizontal direction, since they don't balance, we're going to have the applied force competing with friction, and the effect is that the mass will accelerate in that direction. Alright, a 2,000 kilogram elevator is moving. The tension of the elevator cable is 10,000 newtons. But I know that's nothing compared to the tension in your heart as you're trying to figure out how to do this problem. Okay, that was reaching. Alright, so let's get the weight of the elevator just because we can, because why not? So Fg, that's going to be 2,000 times 10, which is going to be 2,000 newtons, of course. And now we'll get this elevator that's accelerating. So let's just actually figure out what's going on here. So we're going to have this tension force, and we're going to have this weight force. And let's just go ahead. Let's assume that the elevator forces are not balanced since it's accelerating. So we'll say tension competes with weight, and the effect is that the mass accelerates. So we're going to have this 10,000 newton force competing with 20,000 newtons, and the effect is that this 2,000 kilogram elevator is going to accelerate. When we actually solve this out, we're going to get that the acceleration is negative 5 meters per second squared. So this means one of two things. Either we are moving down and speeding up, or we are moving up and slowing down, because in both these cases, the acceleration is downwards. So that's number 3. Sorry, Alright, let's go ahead. We've got this 50 kilogram person pushed along a floor. Here's the velocity plotted as a function of time. And we're going to assume that there's friction. So let's draw a free body diagram here. Whoops. Little pen tool, draw us a free body diagram. So we're going to have a normal force. We're going to have a pushing force. By the way, just so you know, if you get the PDF file of these solutions, they're actually like typed and drawn, so it doesn't look this atrocious. Now, notice something. From 2 to 4 seconds, we've got an acceleration here. So let's actually get that from the slope. And when we do that, that's going to be rise over run. So that's going to be 2 minus 0 over 4 minus 2. And that's going to give us, 1 meter per second squared. So let's go ahead and get the force. So we're going to have force of the push minus the friction equals ma. And it's a 50 kilogram person, so we're going to have 200 newtons.
Good afternoon.
And now we'll go ahead and subtract the friction force, which we don't know what it is. That's what we're going to calculate. Whoops. And then it's going to be 50 times the acceleration of 1. And that's how we're actually getting the friction force is going to be equal to 150 newtons. Now continuing, let's go ahead and assume that the force of friction remains unchanged from part A. Well, if we look here from 4 to 10 seconds, whoops, let me scroll up here, we actually have a constant velocity from 4 to 10 seconds. So what that means is the pushing force is going to actually balance the friction. So we're going to have Fp equals F, and that's going to be 150 newtons, because constant V means the forces balance. All right, now let's review this motion map problem really quickly. So let's just go ahead. So we want to know the displacement and the velocity at these various times, and from that we're going to build a motion map. So kind of working with this. So at 2 seconds our velocity is 0. If we read it off the graph, that's just terrible. Yeah, 0 meters per second. Then we are at 4 seconds, we're at 2 meters per second, and we continue at 2 meters per second the whole time. Now for the displacement, we need the area. So at 2, we actually have a displacement. Let's just get the area of this triangle here. That's going to be 1/2 times -2 times 2, which is going to give us -2. So we have a displacement of -2. Then at 4, we add the positive area back, so we get 0. And then from 4 seconds, so at 6 seconds, we have -2 plus 2, which is 0, plus, now we have 2 here, times the height here, which is 2, which is 4. Then 8, and then finally 12 meters, assuming I did my math right. So based on this, we're going to do a motion map. And so what that means here, if we draw our motion map, is, and I gave you this thing that starts off at 0. So if we were to start at 0 seconds, then at 2 seconds we're going to be at -2. And then at 4 seconds it's 0. At 6 seconds we'll be at 4. At 8 seconds at 8. And at 10 seconds we'll be at 12 out here. So again, this is 0, 2, 4. You know what? I don't like that. Let me change the color so that we get the time and the position distinguished from one another. So this is 0 seconds, 2 seconds, 4 seconds, 6 seconds, 8 seconds, and 10 seconds right there. All right, so that's the motion map.